Hello, hello. In the previous video, we created all the static information we need about the registers that is right here. And in this video, we will interact with the registers of the process that we are trying to debug. Each process that runs on your system has its own data and registers. And at one point, there can be the data of only one process. So when CPU switches contexts between processes, it copies the data of the process from RAM into registers, and after processing, it copies out the data from the registers into RAM, making place for some other processes register data. So each process has its own set it has its own collection of data that is stored in registers when the CPU is working on it. So we need to create, so we'll create a struct, and that struct will be responsible for all the register data of the process that we're trying to debug. We have a process that we're trying to debug, but right now the data of this process that is stored in the registers is not stored in my debugger memory anywhere. So we'll create a struct. So let's do that. Let's create a new file called process registers.rs, and what I'll do is I'll create a pub struct proc registers. All right, and let's say it has some data. And can you guess what the data type of this is going to be? We already created it. It's just user, and it's coming from this register info. But to be able to import it, I need to make it public. Where is it? So let's make it public, and let's also make this pub, and let's also make this pub. Let's go back to proc registers, and let's now try to import it. All right, that is going to be the struct that I was talking about. Let's also implement some functions that will make our life easier when playing around with this data field right here. So I want a function that will create a default empty user object that I will need when I create a object of this struct proc registers. So right now, if we go to user, if I want to create a default object with everything zero, I don't have that right now. I'll have to provide value for each of these fields, and it's very cumbersome. So I'll create a method that will do that for me. I will fill the data into that object when I read from the registers. So first I want everything to be zeros, and then I will read from the actual registers on the system using the ptrace command, and then I will save that data in this data object right here. So what I want is I want a default implementation of user default constructor that will give me an empty user. So let's go to user, and I will impl user, and let's call it pub fn default user, and it returns self. And we're going to use a standard library to do that, to help us create an object with everything zeros in it. So this creates an object, and I want only zeros. Std uh, mem, and let's call zeroed. We're calling in, so this function needs to be unsafe, pub unsafe. All right. And I also want a function that will print this user object in a human readable format. So in a pretty format. So pub fn print, let's call it user, and it takes a self, the object that we're trying to print. And right now I'm going to copy paste a lot of code. I'm copy pasting it because it's just a lot of println statements, because you see user has a lot of fields, and then it has nested fields. So it has a lot of fields. So I'm just going to copy a lot of print line statements for you. So you can copy that and you can find that code in my GitHub. So let me copy all that and let me paste it right. So this is all that code, everything that is required. Just printing. So I'm printing the values of these registers, then printing the value of these registers. That's it. And since these are in a list, so we're just looping over them. So that's it for the human readable thing. This will be quite helpful. We will use this function in at the end of this video to see if that we are actually reading the values from the registers. I'll update some values in the registers and then I'll read and show the values to you again. So that's where we will need this function. It's not actually necessary, but it's quite handy. Anyways, after this, we need to access all the registers to actually update them outside of this module. So let's make all the members of the user regs struct public. So I want to access all of these outside in the proc registers module. So need to make everything here public. Also make the struct public as well. Uh, and let's make these public as well. Where's the user struct? Let's make these public as well. Just in case if you ever need them outside of this uh, module. All right. We will also access the properties of register outside of this module soon enough. So where is register? Yeah, right here. So let's make these public as well. And now we want to make a function to create objects of proc registers. So I want to impel a constructor for it. So I will implement proc registers and I will say, let's just call it new. And since it has a data field in it that's of type user, so it takes a user and we'll return and it's going to return self. All right. And where is that? Where is user? Sorry. Self is not required here to return an object of. This will return an empty object for us. Now this proc register struct is supposed to be associated with a process. So we'll add it to the process. I will add a public field and I'll call it proc registers and it's going to be of type import proc registers. And since we did this, we will also need to update the constructor for process. So where do we have it? Right here. This is now going to take another field, and that is going to be the object of proc registers. Let's call it proc registers, and right here since we updated this constructor, we will also need to update anywhere this constructor was being called. We already have an error for it. So right here, it expects another property that we need to pass to it. So let's create that. Let proc registers equal to proc, proc registers and oh, sorry, proc register. We're creating the proc register, right? So it takes proc an object of proc registers. What does it? Hmm. What I'll do instead is I will take data, and it's going to be of type user. And what I'll do is I will create let proc registers equal to proc registers, and it takes data, and that is fine. So we need to call it. Where is it? Where is the error? Right here. So right here I need to create let data equal to user, default user, add and save to function, and let's pass it in. Copy these two lines, go to the next error right here and paste. So that constructor was being used in the attach and the launch functions that we have now updated. So when we do this, we will also need to update our test cases. If you were to go and see, our test cases will now be failing. WSL, just wait a bit. So cargo test, this will fail. So let's go to tests, and hopefully this will show me where the error is. So right here we need to pass in uh, the same thing, right, that we copied just a second ago. So let's just paste that. And what's the error here? Process.attach unsafe. Okay, sure. And what's the other error? Again, unsafe. So surround with unsafe block. All right, so let's try to run our tests again. Hopefully it works this time. What's the error? Call to unsafe function right here as well. Where else? In main, surround with unsafe, and where else? I guess that's it. Cargo test. So now our tests are working fine now. So now the proc registers struct is associated with the process struct right here. So now each process has its own set of data. Why I created a different struct here instead of just having a data field right here is that I single responsibility principle basically. I want this process registers to have the responsibility of playing around with this data field, and the only thing that process will do with these registers is flush them down uh, to the actual registers or read the value from the actual registers into this field. That's all I want this process to do, and this proc register will have functions that will play around with the data inside of this field. So I wanted those two responsibilities to be segregated out. So I want to write functions that will manipulate user and proc registers. The process and the proc register structs, they are going to communicate with each other, and they are going to pass around values. So the process is going to pass around values to process registers to store them in data, and then data is going to read a particular value from this data field and give it to process to actually feed it down into the register. So with a debugger, we can update a variable's value. So this will need to read a field from this data field from maybe one of these values, and then we're going to pass it down to process, and then this process will actually update the value in the actual physical register. So these two structs are going to communicate with each other, and it's better to encapsulate the data type they are going to use to communicate with each other. And we'll do that. What I'll do is I'll create a wrapper for the value, and it's quite convenient to do that in Rust. We can use enums. So I'll create an enum, and we will use it like a discriminated union. So depending on the type, we're going to process the data differently. That's what a discriminated union does. So we'll see that soon. But right here, I'm going to create an enum, and let's actually call it register value. If you were to go back and look at the register format enum that we created, this defines the type of data that is stored in registers. So it may be a uint, a double float, a long double, or a vector. You'll see this long double. Now this is a valid data type in C++, but not in Rust. So if you want to play around with long double in Rust, you need to use an external dependency, and it's called F128. So we'll add it cargo add F128. So this will add that 128 bytes float, that is basically long double, and then we can import it and use it as a data type. So going back, the possible values that we're going to send back and forth from process to proc register and proc register to process are the following. So U8 is going to be a U8 value, quite simple. And similarly, U16 is going to be U16, then U32 is going to be U32, then U64 is going to be U64, then we have I8 is going to be I8, then I16 is going to be I16, then I32 is going to be I32, then I64 is going to be I64. Those are all the ints, and that are all the possible ints that can be passed around from process to proc register and vice versa. The other are floating points. So float is going to be F32 in C++ land, and then we have double. So double is F64, and this is why we needed the dependency, because we do not have F128 built in into Rust. So this is the data type that we need for long double, my bad, float double, long double. And the other thing I showed you in register format was register format is vector. Now this vector can be of 64 bytes or 128 bytes. So we'll create two here, and byte 64 and byte 128. So a 64 byte can be represented by an array of bytes and 64 bits, sorry. So U8 is 1 byte, and then 8 bytes is 8 to the 64, 64 bits. And then similarly U8, and it can be 16, so that will be 128 bits. We should also probably create some helper functions that will help us use this register value enum so that we can play around with these. So let's do that. Import register value, and what I want to do is write a function that will convert an enum value, an enum variant, to bytes, and then I want to create an enum variant from bytes into an enum variant. So we'll create functions for that. So pub fn as bytes mutable, so it will return mutable bytes to us. So it's going to take an object and mut. Now we don't know what the data type is going to be because it's a lot of variants. It may be any one of these variants. So let's make it a generic function and let's use that data type right here. And it's going to return a pointer to a mutable byte. So it's going to return a pointer to byte and it's going to be mutable. So we can simply convert that by as mute from and as mute u8. So this converts the object to mutable to a pointer of mutable from, and then we convert it into a array bytes, a pointer to bytes. The other thing is and non-mutable. So if you want a pointer to non-mutable, so let's call it as bytes const, and it's going to return, instead of mute, it's going to return a pointer const, and it's not going to return mutable, it's going to return const. And right here also it's not mutable, it's going to be const. The other function was to do the opposite. So pub fn, and let's call it from bytes. So it's going to accept bytes and it's going to be a pointer to u8s, and it's going to return. Now we don't know the type, what the type is, what we expect. So let's make it generic so that we can use it with any of the variants. So let's make it 2. And what we'll do is I will create a pointer that we will return, not a pointer, an object that is zeroed out, and then we will fill the values into it. So like we did earlier with user standard mem zeroed, zeroed. Now this is unsafe, so surround with unsafe and return ret. And what I want to do here is I want to copy the bytes into this ret object. So we will also use the standard library to do that. So std ptr, and what I'll do is copy non-overlapping, and it's going to take the bytes that we want to copy, the object that we want to copy to. So let's give it a mutable reference of ret, and we will uh, coerce its type to a mutable because I want this function to be able to copy things into it. So that's why it needs to be mutable, and then I will make it as mute u8. So we first converted to 2, then we converted to u8, and then uh, the other thing this function needs is the size, how many bytes to copy. So we can get that with std mem and then size of, and this is also a generic function, so we can call it like so, and we can pass in the type this function was called with, and this will give the size. This will copy the that many bytes from bytes to this ret, and then we are going to return it. So these are all the helper functions that we needed. We'll start reading and writing values from and to registers now. The process object will initiate the write using the ID of the register. So let's create those methods. The ptrace commands that we're going to use are namely poke user and peek user. Unfortunately, these commands don't allow us to write to user fpregs. So we have that user fp regs. Unfortunately, the ptrace commands poke user and peek user don't allow us to write to these structs, and that's because all of these are not are not 8 bytes. So this is just 2 bytes and this is 4 bytes. These are not all 8 bytes, and that's why uh, the implementation of those commands don't allow us. So what we'll do is we will write a function that will update all of these values all together. So the peek user and poke user are used to fetch and write the value to and from a particular register, and that is not allowed for this user fpregs. So we will create functions that will update this entire thing as a batch. We have this one struct that is one batch, and the other struct is this. So we'll create a batch update function for these two structs. All right, and let's create them in process because that's where we actually want to interact with the physical registers. So let's do that. Let's create the function that will write to user by the register ID. So pub fn write to user by register ID. And what I want to do right here is, so this function will accept a value, and I want to pass that value down to this. I want to update this data field with that value. So it's going to take a mute self, and then let's say it takes an ID, and it's going to be register ID, and it's going to take a val, and it's going to be a register val. So let us get the register by its ID first. Register equals to uh, register, then we have by ID. So let's pass in the ID. So this gets the register for me. We are getting this register because this register stores in itself the data that offset. This offset will be used to figure out how many bytes inside this data are we. So if the offset is 0, then we need to write at the 0th byte of this data field. If the offset is 16, then we need to write at the 16th byte of this data field. So we need that offset, and let user bytes equal to self dot proc registers dot write uh, hmm, to register, write register. I'll create this function soon, and let's pass in the register and the value. So oh my bad, val. So we'll create this function. What this function will do is it will read the offset from this register, and then it will put the value from this val at that offset in the user field, and then it will return the bytes of that user field. That's what I want right here. And if the register type happens to be FPR, like I told you, the peek and poke user don't allow to interact with those registers individually. So we will batch update them. So if the register type is FPR, then I want to create a function that will uh, batch update them. So self dot write FPRs. This will call as a write dot self f. Otherwise, let offset equals to register dot offset, and let's convert it to bytes. We can do that with register value. So we want to get a register value. We know the offset. So from bytes, and I want, otherwise almost everything is U64, and this from bytes register value. Where is register value from bytes? Is it not pub? And it takes a pointer to U8, to a pointer to bytes. So we have user bytes, and I will add to it the offset. So this will give me the U64, the value at that offset in the user object, and then I want to write it to the actual registers. So self dot write user. So let's pass in the offset where we want to write the data and the data that we want to write. So we will create this function as well. Instead of, let's call it bytes. So we need to create this function. Now, unfortunately, uh, this is not as simple, because I told you almost everything is U64, but not everything. Some values are U16, some are U32. The That's what's interesting about the 64-bit x86 architecture. We have 64-bit registers, and then we have sub registers that are 32-bit, 16-bit, and then 8 and 8. So for those sub registers, for the AH, BH, CH, and DH registers, this won't work. The peek and poke user commands, the ptrace peek and poke user commands, they expect this offset to be divisible by 8. The high 8-bit registers are offset by 1 byte into their parent registers. I'll show you what that means. So, so let's say the racks register starts at the byte 160, address 160 in the user struct. So the AL register is at 160, but the AH register is at 161. So it's not divisible by 8. It's not aligned to the 8 byte architecture. So all the other sub registers are aligned. The EAX is 16 is at 160. The AX starts at 160. The RAX starts at 160. But the AH starts at 161. I showed you the diagram in the previous video where AL starts at 161, and then we have AH, and then we have the AX register. So this won't work. We somehow want to make the AH, BH, CH, and DH registers also align with the other registers. I want them also to be aligned, and I want them also to be the offset for them to also start at 160 somehow. We can align those addresses using some bitwise operations. All right. What we can do is let offset equal to offset, and we can bitwise AND it with 0B111. What this will do is this sets the lowest 3 bits in the offset to be 0, and that makes it aligned with 8 that makes it aligned with all the other registers. Just remember that you have to do this. This is uh, some ceremony code that you have to write. What this function will do is it will take an ID of the register, it will take a value. We will update that value in this object right here. Then we will get the data from this user object, and then I will write it at a particular offset in the register, in the actual physical registers. So right now I haven't implemented this write fprs and this write user function, but those function will be responsible to actually drill down the data to the actual physical registers. One other function that I want is a function to read a register value by id from the actual physical registers. So pub fn get uh, by id, and it takes a mutable reference to self. It takes an id which is the register id, and then let us get the register. So by id, let's pass in the id, and then I'll create another function get register val, and it takes the register. We don't have this function yet, and I wanted to return a register value. So what I'll do is this may fail in case the offset is incorrect or something like that, if the id is incorrect or something like that. In that case, I want to return an error string as well. So register value and str. So in case of error, we are going to return a string that tells us what the error is. So of so we right now have 4 functions that we need to create: this write register function, this write fprs function, this write user function, and this get register val function. Of these, the logic of getting the register value from the user struct using the register offset is simple. So let's implement that first. We already have the offset where the data of the register lives and the size of how many bytes the data is. It's all stored in the register, right? We can read the data from the user struct by getting a raw pointer into the user object and then skipping the first offset number of bytes and reading the next size number of bytes. We can then cast the bytes into a register value depending on the format of the register. In Rust, we can get a pointer to the first byte of an object by getting a reference to it and coercing it to UART like we have been doing so far earlier as well. Where did we do that? Yeah, right here. So this is what gives us raw pointers into objects. So we will do that. So first of all, I need a function that will not register value. Want a function that will get a value from this data field for a particular register. So pub fn uh, get register val and it takes a reference to self and then register, and it takes a register and it's going to return a result of my bad, sorry guys, we don't want this function here right now. I want this function in the proc register struct. So this is just going to return a particular register. So if you were to go, this is the function that we want to implement, and this doesn't even need to be public. So right now we haven't implemented this write register, write FPRS and write user right now. We will get to it soon. I want to first write this, implement this because it's simpler than the other thing. And at the end, I will show you the entire flow of the code. So what we want to do right here is, I want to get a raw pointer, and I already have a function that is doing that for me, right? So getting a point. Okay, so this will work. So let bytes equal to register value, and as bytes self dot data expected. Why is it taking a mutable reference? Let's remove that. Should not take a mutable reference if it's returning const. So it should be taking const. Huh. So we know the offset is uh, register dot offset, and if the register dot register format happens to be register format of uint, in that case I want to also shouldn't I derive some, yeah, I should, uh, we should derive all of this for any enum. So right here what I'll do is I will match on the register size, and depending on the register size I will create objects of u8 or similar things. In case of one, I want to one means 1 byte, I'll create objects of u8. If it's 2, I will create objects of U16. If it's 4, then U32. If it's 8, then U64. Otherwise, we have an error. Uh, Otherwise, we're going to return error of unexpected register size. And in case this let val equal to register value, we already have that helper function from bytes, and I want to create object of u8. So let's pass, so give it the type u8, and let's pass in bytes dot add the offset. And in case everything is fine, I will return an OK of val. This is a u8, so register value u8, and then val. What's the error here? Calling an unsafe function. This should be unsafe. Unsafe function. Make it unsafe. All right. Hmm. Similarly, for 2, it's going to be U16. Oh, sorry. 16. Right here is going to be U32. Right here is going to be U32. And right here is going to be U64. So these will be the ints. If the format is not uint, then the format may be else if register dot register format, it may be so we have double float, long double, and vector. So double float. So handle double float. If the register format is double float, we will create an object of F64. So we don't have, it's double. Okay. But if the format is else if register dot register format is long double, in that case let val equal to, let's just copy this. In that case it's going to be F128, and it's going to be long double. Now the other thing can be else if register dot register format equal to register format of vector, and register dot register size happens to be 8. In that case we'll get 8 bytes. So let's just copy this and let's give it the type u8 and it's going to be 8. And instead of long double, it's going to be byte 64. Else, we can create an object of byte 128. Make it 16. So we implemented the read functions because even though this code may not seem simple, it is simpler than the code. The write code is much more complex. The write is going to happen when we want to update the user struct, and then I want to flush those values down to the registers. And writing to registers has certain issues. Uh, we can't write a 32-bit value to a 64-bit register because 32-bit values, when they are signed, their bit representation is quite different. For unsigned integers, it's the bit representation is same, and we can just copy the first 32 bits into the 64-bit register and then zero out the rest of the 32 bits. But it's not as simple for signed integers. Uh, to write negative numbers to registers, we need to use something known as the 2's complement. And now this is something that you would have probably learned in college in the very basics of computer science or maybe even in school. Let me still give you a reminder of what 2's complement actually is or what it looks like rather. So this is what the 2's complement looks like. What that means is the first uh, bit can be used to represent the sign, and then the rest of the 7 bits will determine the value for signed integers, but for unsigned integers it obviously won't. So for unsigned integers the values can go from 0 to 255. For signed integers the value can go from minus 128 to 127, where the first bit defines the sign and the rest of the 7 bits gives us the maximum possible value of that number. We can change a positive integer to a negative 2's complement integer by flipping all the bits and adding a 1. This is also something you would have probably hopefully learned in college. I certainly didn't. I had to research it a bit. But anyways, this is still simpler. It gets even more complex when we are handling floating point numbers. According to the IEEE standard, one bit of the bit representation of the number is going to be used for sign. 11 bits are going to be used for the exponent. What that means is 11 bits are going to decide the position of the decimal, and then 52 bits are for the actual value, the actual numbers. So 52 bits are used to decide the digits, 11 to decide the position of the decimal, and 1 for the sign. We want a function that can convert a number from its smaller bit representation to larger bits so that we can finally store them into the registers. That's why I haven't implemented these write functions right now, because we want that function first, something that will enlarge a number from 32-bit representation to the 64-bit representation. So when we get a floating point number, we will need to handle the fact the IEEE standard. Since we don't know the value that we want to convert, we will also use generics for this use case. And the function will take a register object to know the format of the register we are writing or we are working with. So let's create that function as well. I will create that as well in the register value, Before we do that, I see that there is an error, and if you were to hover over it, you will see that EQ is not implemented for F32. So just remove EQ from here, and that should take care of the error. And the function that we're going to implement, let's call it widen, because that's what we're trying to do. We're trying to take a smaller number and widen its bit representation to fit into to be 64 bits. So we're taking a 32 bit and widening it to 64 bit. So let's create a pub unsafe function, because the things we're going to do is going to require std and most of those functions are not unsafe. So pub fn and widen, and since it's going to be generic, let's give it a from. All right, and let's I told you that it's going to take a register because we want to know the format and the size of the register. So then it's going to be a reference. Let's just say it's a reference. It's not taking the ownership of the register, and we're going to receive a value that we need to widen. Let's just call it t, and it's going to return 64 bits, and 64 bits are just uh, 8 8 bits. That is 1 byte multiplied by 16, 64. That's what we want to return from here. And let me fix the name register. I hope all of this was visible. I should have increased the size of it way sooner. So what we are going to do is going to depend on the type of number we are working with. If it's a floating point number, then we have a different algorithm that we want to apply to it to make it 64 bits. My bad. I'm saying 64. What I mean is 128. Anyways, uh, because 88 is 64, 64 into 2, 120, 128 bits. So if it's a floating point number, we need to do a different thing. And if it's not a floating point number, if it's signed, we need to do something else. If it's unsigned integer, all well and good, we can just easily convert it. But if it is floating point, let's handle that case first. If uh, register value, we'll create another helper method, and that will let me know if something is a floating point number. Floating point, and let's give it the type from. If it is floating point, then we're going to do something. So let me create this function, create associated. Why does it do that? Let me remove that register value. You bring it down here, it returns a bool. What's the error here? Remove redundant generic arguments. No, but my function is going to be generic. My function is going to be generic. So let it take a t and let it return a bool. So we'll implement that soon enough. But if the number we are working with is floating point, then I should check the format of the register. So if the format of the register happens to be double float, uh, that is double float corresponds to F64, then convert it to uh, we'll convert to the to 128 from 64. But if the register format happens to be long double, we can simply copy, because both of them are essentially 128. Because long double is F128 for us. In any other case, uh, if we have a floating point and it's not F64 and not F128, we'll create a helper method that will help us convert things to byte 128, and that's what we're going to return from this function. So let me check the format of the register. So if the register format, it happens to be a register format of double float, in that case, I told you we're going to use the standard library, and the standard library has a helper method that will let me copy the bytes, uh, std mem and transmute copy, and I want it from the type from and F64, and let's give it a reference to T. So what we're trying to do is we're trying to copy. What this will do is it will copy the bytes from this format to this format, transmute copy, that's what it does. And F64 will be the format of the register. We get the F64 because we entered this if case after checking the register format, and if it happens to be double float, we know that corresponds to F64. What this transmute copy function does is it casts T to F64 and convert the byte representation under the hood. That's what this does. And now I will create a function in register value itself that will help me uh, widen, like basically it will convert anything I pass to it to byte 128, because this is a 164 and it can simply be copied into byte 128. So to I'll create this 128 function and it's going to take the value, and whatever we get from this we're going to return. So let me help IntelliJ with completing this function for me. Create associated function. Why do you do that? All right, so and byte 128, it's also going to be a generic function, but the generic will be auto. The Rust compiler is smart enough to understand what the generic is here, so we don't need to explicitly mention the generic here. And let's just call it bytes, and it's going to be from, and it's going to return this. Uh, if that is the case, then fine. But else, if the register format happens to be register format of long double, in that case, do this. But instead of F64, it's going to be F128 of 128. Good. This casts T to 128 and converts the underlying bit representation. Otherwise, we can simply convert it. So register value to byte 128, and let's just pass in the T, because it's lower amount of bytes. We can simply convert it to return. It's not required here now. Not required. All right. But if the format is not floating point, else if register. Hmm. So now we need another helper function that will let me know that if a number is signed or not. We don't have that right now, is signed, but I'll create it soon enough. And it will take the data type. It's going to be generic as well. And let me create that function actually. Is signed, and it's going to return a bool, and it's not going to take anything because we can tell from the type. If it is signed, in that case, I need to check if it is 2 bytes, 4 bytes, or 8 bytes. So if it is 2 bytes, I will cast it to I16. And if it's 4 bytes, I'll cast it to I32. If it's 8 bytes, I will cast it to I64. So if the register size happens to be 2, that's what I mean. Register dot size. And if it happens to be 2, then I want to do something. And if it happens to be 4, I want to do something else. And if it happens to be 8, then again I want to do something else. And in all other cases, I can do something else. So right here, what I will do is, let me just copy this, and I will cast it to I16, and I will cast this to I32. So the Rust compiler is actually smart enough that it will be able to infer this type here from this type that you see right here. And that type will be helpful in actually converting it to 128. And in any other case, we don't need to cast it. Let's just do this. Let's just say T, and else again, let's just try to convert it to T. And so the first thing is the is floating point. So the is floating point, we can tell that by simply checking the type of the uh, this data type. We just need to check that, and with that we'll be able to. So to, like, this is like reflection in Java. So if you want to check the type and do some logic on type, you do that through reflection in Java. But in Rust, you use something called type ID. So use std of any of type ID, and let type ID equal to type ID of, and give it the type that you're working with. And in that case, I can simply check if it is uh, a float, f32, f64, or f128. And in all those cases, I'll return true, otherwise I'll return false. So type ID uh, of f32, so, or f64, or f128 of 128. So this will let me know if something is a floating point number or not. And we're going to do something similar in is signed. We can know a number is signed by simply checking its type, and if it happens to be I16 or I32 or I64, then we know that it is uh, a signed number. So I16, at least its bit representation is signed. And I64. Okay, now we can finally implement this to byte 128 function. So what we're going to do is we'll create a object, and then we'll copy the bytes into that object. So that's what we'll do here. So I'll create the let mut result equal to, and it's just going to be zeros right now. So 0 u8 comma, and it's going to be 16 because 128 bits I want. Then I will get a raw pointer to the bytes that were passed to me. So let ptr equal to uh, bytes. I will get a raw pointer to it as const from as const u8. Then I will check the size of it, because that's how many bytes we need to copy. It's going to be ptr std mem size of, and I will give the type from. That's how many bytes we need to copy, and then we'll call the std ptr and copy non-overlapping. We've used this function before as well. ptr comma we want to copy it into result, so result dot as mut pointer, and we only want to copy 16 bytes, so size dot min of 16, and we just want to return it. What is the issue right here? But found, oh, uh, u8 2 expected u8 of 16. uh, Calling an unsafe function, add unsafe. uh, we are forcing to only copy 16 bytes because the type that this function may be called may be with a vector, because uh, right here the control may come here if this from is a vector, and in that case I only want to copy 16 bytes, and if the vector is larger than 16 I don't want that to be copied. That's why we are forcing this limit of min. So now we can finally use this widen function to write values to the user struct. We created the register value enum, and I told you we are going to use it as a discriminated union, and we'll do that in the proc registers. Impl proc, where is impl proc registers? So right here, what I want to do is I want to widen a value. So this is creating the value for us, and here I want to do the opposite thing. So I will create a function, and it's also going to be unsafe, and it will be write register, and this is the function that I'm trying to implement right here. So let's implement this, write register, just so that I'm make sure I'm not making any mistake, and it's going to take a pointer to self and a register, and its type is going to be a register. Let's say it doesn't own the value, and the val, so register value, and it needs to return a pointer to u8. It's user bytes, right? So it has to be a pointer to u8, pointer to bytes. So mut u8, that's what it returns. Yep. And right here what I want to do is I want to convert the value to bytes, and then I want to widen it, and after that I want to copy it to the user object. So I want to write the register into the user. So we have that let bytes, it's also going to be a pointer to bytes, and register value as bytes mutable, and we will call it on self dot data, but we need to pass in a mutable reference. All right. Now I need to know where to write this value, at what position, and that will be the register offset, and we have that in register dot offset. The other thing I want is how many bytes to write, so that will be register size, register dot size, and right now what I'll do is I have the value and I will widen it to match the register size. So I will uh, match val remaining parents. All right, and let's say it returns the widened value. So hmm, so this is going to be the user bytes, and this is going to be the val bytes. All right, and let's do this, and it's going to return. And if it is U8, I want to just uh, register value of widen and register comma v, and the Rust compiler is smart enough to infer this data type from right here. So that's all I want to do for each and every one of them. Let me copy this, paste it right here, paste it right here, paste it right here, paste it right here. We are doing this because this will uh, I just wanted to pass in the data type into widen, and the compiler will help us do that and make it. So this will give me the val bytes. Now I just want to copy these val bytes into the user bytes at this position, and I want to copy this many bytes. And we have a standard function for that, standard library. So standard ptr copy non-overlapping, and right here, after this, after copying, I will return the user bytes, and I want to copy the value bytes, and we need to give in a pointer, and I want to copy it into user bytes, but I want to copy it at a particular position. So we'll add the offset. It's reg offset, and I want to copy this many bytes. This copies all the bytes into the user. Now this, I told you, in proc register we will only write the logic to interact with the user object. The actual logic of flushing the value will be in these functions. This write register, so this write, not write register, this write fprs and write user. These two functions will actually flush the value down. This write register was only to interact with the user object. So we are using these functions, but we haven't created them, right? Or have I created a function with to do? I don't think I have created these. Let me check. Write user, it's not there, so let me do that. Uh, Create method, very good. And let's say self will be self, and then this is the offset, and p1 is the byte or the data that I want to copy. And right here we will use the ptrace command, but the ptrace command, the Rust version doesn't support the peek and poke user. We need to use the C version. So use nix libc, that means the C version. I want to import the ptrace and the ptrace poke user. Ptrace uh, poke user, and so I wanted to import these two, and we'll use these to actually flush the data down to the registers. So let result be, and we'll use the ptrace command, but it is unsafe. So let's mark it unsafe. And right here, we use the ptrace, and I want to use the ptrace poke user. and it needs the PID. So self dot PID dot as raw, and then it needs the offset where the data needs to go and the data that needs to go there. Data, and I'm getting this result. This result will be a negative number if writing to that offset failed. So if result is less than 0, uh, we will panic. And let's just say couldn't write to user. So that will be the write user function. I told you we're going to create this write FPRS, but with alongside write FPRS, I will also create a batch update function for the GPR, the general purpose registers. So let's create this method. And for FPRS, we're going to import this, but instead of poke user, we are going to use the set fpregs. So ptrace set fpregs. Uh-huh. And going to use the same uh, structure right here because it's also going to return a negative in case of an error. And if that error happens, I'll say couldn't write floating point registers to floating point registers. All right, and we can't give the offset. We don't have the offset. So, and we don't have the data. We have the data. It's actually in self.proc registers. Let fprs is equals to self.proc registers dot data dot. These are the floating point registers, and we'll use these to find this offset. So the offset is essentially going to be like I want to write at the 0th position of this. So just copy and paste the line that I'm going to give you. Just copy and paste this. This is essentially null because I want to write at the starting wherever this FPRs starts. So and instead of poke user, we're going to use fpregs, and the data is going to be this FPRs. And but I need to pass it in as a pointer. We've been doing this already, const, and because we don't care about this type, so I'm using an underscore, and then as a const of now this thing requires a particular data type that is something that is there in C. So just copy paste and that as well. All right, that is the FPRs. Typo rename to FPRs is fine, and I also need a GPRS function. So let me just copy and paste that, and instead of I1387, it's going to be regs, and instead of fpregs, it's going to be simply set regs. So I'll remove fp, copy, paste. What's the issue? GPRS. Make it GPRS. GPRS could not write to general purpose registers. Purpose registers, rest everything remains same. And this much duplicate is fine. Uh, so we have written all the code that's required to write, but I still need to write the code to read all the register values and actually store them in proc registers. We don't have that yet. Uh, so we need to do that as soon as we start debugging a process. So let's do that. I'll create a function in process that will be reading all the registers. So let me do that right here. pub fn read all registers, and it takes a pointer to self, mutable pointer, because we need to write. And similar to this, we also need, this was ptrace set regs. I need here ptrace fpregs. So this was set fpregs. I need the get fpregs because all those the fp related things all need to happen together. Ptrace get fpregs. Uh, all the others can be handled with the normal ptrace that we have, the Rust version of the ptrace. We have that right here. Next says only for fpregs do we need that libc version. So I'll call it as libc ptrace. All right. But to get the normal general purpose registers, I'll simply use the ptrace that we have up there. So let uh, regs equal to ptrace get regs, and I just need to pass in the pid, and this returns a result, right? So let's say unwrap or else, and in that case I will just panic. uh, Panic, and I will say couldn't read GPR registers, and just give whatever the error was. E. Now I just need to copy the data from this regs into the self.proc registers. So self.proc registers dot data dot regs equal to user regs, a new. So we created this by emptying out everything by simply stdmem zeroed. Now I actually want to give in data, so just copy paste. We just need to do regs dot something, and we'll copy it into this data type. So my bad, guys. Remove the NBSP. Just copy it in. Instead, let's just rename that regs libc. And now we need to read in the FPR, the floating point registers. So let mut fp regs, and it's going to be unsafe. I will create an empty object that I will read into. So it's going to be user fp regs struct, and I'll just create an empty route thing std mem zeroed, and let result. Uh, so this result will be the same thing. This will be instead like this thing, but instead of set, we'll use the get and put a semicolon right here. Instead of set, make it get, and fp regs. Everything else remains same, and if result is less than 0, could not read floating, could not read, and that's fine. And if we were able to, else self dot proc registers dot data dot equal to fp regs. So those are all the fp regs. Now we need to read in the debug registers. So let dbr dbrs equal to, and the if you were to go in and look into the user struct, it's just a list. So where is it? Where is the user? So the debug registers is just a list. So its data type is u64 and 8 of them. So mm, what I'll do is I will loop them and read them one at a time, but I need all the IDs. We have that function, right? Read register by ID. So we'll use that to get the offset of a particular register. So register ID of dr0 and say 0, 1, 2, 3, 4, 5, 6, 7, dr7. So for I comma id in dbrs ids dot iter dot enumerate, and let register equal to uh, register by id, and let's pass in the id, and we need a point register. I need to re-reference it. So id, and the command that reads individual registers, it doesn't return a negative one like in the above cases. It just simply writes to the error now standard output. So we need to first clear that and clear. And if after reading error now happens to have something, last is not equal to error no of unknown error, basically no error no, in that case couldn't read dbr uh, debug registers. We won't know which one debug registers, but if that didn't happen, I can just proc registers dot data dot u debug reg equal to, I want a variable that will be u64, and I want it to be at a particular index, and the index will be I. So let's read data one at a time in this for loop. Let data equal to, now again it's an unsafe operation, uh, lib regs libc ptrace. I'll call it with ptrace peak user, and need to give it the pid self dot pid dot as raw. Then I need to give it the offset of the register dot offset, and it knows what to read. So need to give it the same thing that we were giving to floating point registers up here, the same thing right here as well. So standard null mutable pointer, the C thing, and that's what we need to write to the debug registers. So we have the entire thing now, and I can show you the entire code flow. Let me go through it first. So we first attach to a process. Hmm. Okay, let me demonstrate it. So we have the wait on signal. I told you we'll start reading the value whenever we start debugging, and we start debugging when we uh, wait on a particular process. So if this is an wait on signal, we wait result. Okay, status. We update the status. So let's call self dot read all registers right here, and then I will do. I created that function to print the registers, right? So proc registers dot data dot print user, and after that I will update a particular value unsafe self dot write to user by register id, and let's give in the id of racks. Let's just update the racks register, and I will give it a value of a random value register value. Let's say let's make it u32 and give it 612, and you'll be able to see this 12 when I print it. And print line, and after updating I will do another read all registers and another print of registers. All right, read all registers, but we should also do this in the main function, because that's also where we start to debug. That's actually where we start to debug. So whenever we hit a wait, a breakpoint, that's also a point where we need to read all the variables. But this is also, so instead of self, it will be process, 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 and let's try to build it. Cargo build, and hopefully it works. So it doesn't. What is the issue? From main, oh my, I know what the issue is. The issue is that we need to specify the lifetime, and let's just say it is static. And if it is static, it, I guess it needs to be static where we are calling it as well. So let's make all of them static, because we are only using them with predefined variables or something that we are importing. So let's give it a from, and 2 byte 128. So this doesn't need to be static, but is signed, and floating point, they need to be static. And then we are calling them right here. This also needs to be static. We are just calling them with predefined built-in variables. So that's why cargo build. And what is the error? What's the error here? Where is the error? I don't see the error. Clear cargo build. The error is right here. Self dot, because move happens here. So this is in RDB process. Show me where. What do you mean? Self. So this is in write FPRs. So if a move is happening, just add a pointer. And what else? So add a ampersand right here as well. Does it build? Beautiful, it does. So let's start a test process. Cd tests dot slash test process. The PID is 4552. Cargo run. So as you can see, right now the code must have come right here, the control flow. Right here, we read all the registers and we print them. So let me control D and clear everything. And cargo run again. So I can go up here, cargo run, where is the output? Right here. So whenever the control comes into the main and the process stops, we read all the data of the registers. This is the data in the registers. All right. These are all the registers, and then we update the register. Then we read and display again. So I told you racks register value. That did the right not happen? Let me do a C and let me break this again. Wait, what happened? C, control C. All right, so here we should see the updated value in the racks register. Huh. So U32 off. Did it not happen? What's the issue? Right to user. Right user. Let's print line. Writing to user. Let's look for this. And let me remove that from main. Let me remove the update thing from main. Add a semicolon. Go to main. And I don't want to update it right here. Print is fine, but let's remove this. In the main, we are just reading and printing. So let me try to debug again. Clear and run. So the control comes into main. Right here, we read all the registers and we print them. The value in this register happens to be this, and the process is running. So when I continue it and I go to this process, does it update the value? Writing to user. Why did it not write to user? Let me check that. It didn't update the value. Why is that? My bad, guys. It's not this. It's supposed to be a not. So we are creating a bit mask. So let's try to run this again. Cargo. Let me clear it. Clear. Cargo run. So when we print all this, control comes into main. We print all the registers. We read all the registers. What happened? No such. Huh? 4552. All right, so the value in racks happens to be this. So the control comes here. We go into read all registers. Right here, we use the ptrace commands to read data from registers. We put it into self.user, self.proc register, the user object in there. We update all the values using ptrace commands. Then after that, we print it, and now the process is running. I can stop that process. We go into this debug, so I can continue that process with continue. And as you can see, the process is running. I can stop this process with the control C. This will have awakened my debugger again. And when that happens, we actually come into this wait on signal. So right here, we went into this read all registers. Then we printed these registers. So you should be able to see 4552, this value. Then we should see this value again. We see this value again. And then we go into this write to user by register ID. What this does is it calls the proc user write register function. What this write register function does is it takes the value, it widens it, and then it puts it in the user object. Then we take that updated user object, and if the register type happened to be a floating point, we update all the floating point registers. Otherwise, we update the entire user. We update the entire user. So we do that by using a ptrace command. So you should be able to see this right here now. If I scroll down, we do. And as you can see, the value of the racks register has been updated. It has been updated. Uh, it has been updated with the value that we gave right here. If you were to make it 8, you would have seen an 8 here. So now we are able to read values from the registers and write values to them whenever we want. So that's it for this video. It's been a long one, and I'll see you in the next one.